So today is the last day of radiative transfer for you all. So just a brief recap of what we have learned over the last three lectures. First is we studied what are the equations of radiative transfer. Given an intensity distribution somewhere or the emission at some place, if the radiation has to travel to us, how does it travel and how do we mathematically quantify it? That is one thing. We've understood the basics of connecting the quantum mechanical transitions to this emission coefficients and absorption coefficients through the Einstein coefficients. That is the second thing. We briefly touched upon black body radiation with a focus on how do we characterize the emission from the black body radiation in terms of the radiative transfer coefficients. Third one. Next, we transitioned into relativistic charged particles moving. What is the emission from moving charges? What gives rise to the emission from moving charges? What is the equation for that? And then one important concept that we touched upon is the concept of beaming of radiation. So if a charged object, if an object is moving at relativistic speeds, emission coming from that object is beamed towards the direction of the emission. Then one of the applications of all of this that we did was synchrotron radiation. So forget the mathematical details of whatever we discussed. The basic premise is what you should remember. The basic premise is if there is magnetic field somewhere in the universe, if there are relativistic electrons, these are non-thermal. I will keep on insisting that these are non-thermal electrons, but it goes in your head. There's a big difference between thermal electrons in magnetic fields and non-thermal electrons in magnetic fields. When we call it non-thermal, when the electron distribution or electron gas is not a Maxwell-Boltzmann distribution. We will now look at what happens when there is a thermal distribution. So when there's a magnetic field, there's non-thermal electrons. We've seen that we have one form of radiation called synchrotron radiation, where as the relativistic electrons gyrate around the magnetic fields, they give out beam radiation along their path. You integrate the radiation all around the orbit, you get some spectrum of radiation, that's synchrotron. Now, synchrotron is widely used both in very nearby sun as well as distant galaxies, and that is very wide common topic in radio astronomy. So synchrotron is important. So again, besides the mathematical details, some of the basic properties of synchrotron are the electron distribution has to be composed of relativistically accelerated electrons. The typical distribution, typical ranges of values of Lorentz factors of these electrons range from gamma 100 to even gamma 10 power 6. So gamma 100 to 10,000 Lorentz factors, they typically give you emission to the order of a few hundred megahertz to a gigahertz range. And how am I doing that? By calculating the critical frequency, which depends on square of the gamma and the magnetic field. Okay. So you find the critical frequency where there is a peak of the electron distribution of the synchrotron spectrum. You find what is the typical mapping the electron energy frequency. Rough map. Another point of synchrotron is usually these electrons are found as a power law distribution. So power law in energy. And if there are a power law in energy, there will also be a power law in the frequency space. What I did not discuss is in practical applications. So this is the textbook application. So this is the electron distribution. What is that? It's textbook application. It's a power law. In practical applications, it's like this. Why? Because now consider each of these bins. I purposely made them nonlinear because when we actually do it, we do that in logarithmic space. It's easier because it goes from 100 to 10 power 6, wide range of the energies. So what happens is the power lost by the electrons is proportional to gamma squared magnetic field squared. It is gamma squared. You consider these as small bunches of monoenergetic electrons, each of these energy bins. These electrons will cool much faster, will lose energy much faster than these electrons. So what happens is eventually the entire spectrum, so you start off with a spectrum like this, the entire spectrum starts to decrease, but the decrease in these parts are much more faster speeds. So in practical applications, you have the electron spectrum looking like this. When the frequency spectrum of the flux versus frequency, that also looks like this. So we have often end up with a power law phase here and a cutoff. It can be approximated as a broken power law, two power law, but it's not. But usually we fill in models of the electron decay and then put in the synchrotron solutions to get this figure. So the reason why I'm telling you all of this is these electrons, the rate of cooling depends on the energy, but there's a finite rate of cooling that you can calculate. So if you can find out what is the part of the spectrum of the electron distribution where it starts cooling much rapidly, that naturally gives you a time limit up to which these electrons have been cooling. So this argument, so this will give you this, and this argument can help determine the age of the synchrotron emitting system, which we usually use in practical applications. So the takeaway points are non-thermal electrons, power law distribution energy, power law distribution frequency, and the frequency space can be distorted like this.
Why do the electrons not get thermalized?
They are very high energy. So eventually they would, because you see, I'm saying that I start off with Lorentz factors of 100. These would have very long cooling times because the gamma square compared to the others. If you wait long enough, they will thermalize. You will not see any radiation. So they have to come to gamma close to 1, or eventually mix with the thermal fluid. So there is mixing, of course. The electrons will transfer energy to the thermal fluid, and part of the thermal fluid may also get slowly accelerated by interacting with the electrons. But eventually they will come. But that's a long time.
But you can't have temperatures of gamma.
Oh, of course, these are not thermal because they obviously do not follow a Maxwell-Boltzmann distribution in the energy distribution. It's a power law. Okay. So far about synchrotron. Today we will briefly discuss another emission mechanism. It's called Bremsstrahlung emission. This is also synchrotron is also there in the standard textbooks, but Bremsstrahlung is often more easily understood. So the basic premise of this emission mechanism is you have ions floating around in space, and this is a thermal distribution, not relativistic distribution. So you have a charged particle, which is you have a positively charged ion here sitting there. It has high inertia, so we'll consider it to be at rest. Now you have an electron. Now these are free electrons, okay? Not bound to the ion anymore. Electron trying to approach the ion. Very far away, it will just go in a straight line, not seeing the electric field of the ion. As it comes close by, it will start interacting with the ion. So its trajectory will slightly change. So this is almost, you can say, some sort of a scattering by the ion. It's not exactly the Compton scattering we'll discuss, but a change in the trajectory of the electron due to the presence of the ion. If the electron was initially traveling at constant velocity, there is a change. That means there is acceleration. If there is acceleration, we'll have radiation. So the main point that we want to find out here is what is the nature of the acceleration vector. We put in a standard machinery of Lambda frequency because Lambda frequency has the acceleration square, and we get the total power that is going to be gained. So I have a lot of details here because these slides are taken from my graduate course, school coursework. But I'll try to just simplify and point you to the relevant portions of this. So first, let us look at this equation. This we have seen. This is the radiative term of the electric field. You see, this has u dot, which is the acceleration field. In this particular case, it's often easier to, or in the standard textbooks, you will find that they write it in terms of the dipole moment. So what is the dipole moment here? Charge times the distance, right? So dipole moment of the electron is minus e times capital R. Capital R is the distance of the electron from the location of the ion. So this can be written in terms of n cross dipole moment dot, double dot, which is the double time derivative of the dipole moment or the acceleration vector. This is directly proportional to R. So now I have discussed in the previous lecture that the spectrum, because what we are interested in is not in just the total power emitted, but the energy distribution of the power emitted. So the spectrum is proportional to the Fourier transform of the electric field square, or E omega square. So you can clearly understand that what I would want to do is take a Fourier transform of the dipole moment. This is the basic premise. Now you try to find out what are the acceleration vectors, a parallel, a perpendicular, so transform them parallel to the initial direction of the electron, perpendicular to the electron. You will find that the parallel component is e squared vt. There's a time involved. So the parallel component is short-lived. So it is, if you take the t equals to 0 as a time when you can always scale the time coordinate. If t equals to 0 is a time when the electron is directly over the ion, the parallel component quickly reverses the sign. So if you integrate over the parallel component, that contribution would be very negligible. I'll show you more mathematical details of how that. The perpendicular component of course stays. So the perpendicular component of the Fourier transform of the perpendicular component of the acceleration vector would contribute to the radiation. If you work out the full mathematical details, what we'll have to do is write this in terms of the acceleration vector. So forget about this. That dipole moment is sort of a legacy that is given in the textbook that that's what I've written. You essentially have to find out the Fourier transform of acceleration vectors. You write them in terms of modified Bessel functions. You have expansions, and you collect all the terms of the modified Bessel functions. It looks something like this. Again, you'll find that the parallel component, the contribution for the parallel component goes away. The perpendicular component gives you some contribution, and the total contribution looks something like this. So there is a one term which is e to the power minus omega tau. Tau is the impact parameter by the velocity. Impact parameter is the perpendicular distance between the line of the charge and the initial direction of the electron. This is called the impact parameter. This, by the initial velocity, gives you a natural time scale, which we will call tau. So after working out all of the mathematical details, you will find if the frequency. So what we are trying to find out is what is the emission at a given frequency. So for a given frequency, there is only certain ranges of frequency that will contribute. Otherwise, the spectrum is 0 for omega tau greater than 1. Okay, so this is the final formula of the Bremsstrahlung. I would want you to not look at the mathematical details, but how these are dependent. So what this depends on is, so these are all constants initially, but it depends on the impact parameter and the velocity square. Now this is just for a single ion and a single electron. In our practical system, you'll have a distribution of ions and distribution of electrons. Now for our first case, let us assume that the ions are just standard background distribution. So for a given ion, it will see a sea of electrons floating around. Or say, initially, let's say all of the electrons are moving parallel to each other in a given direction. But they have a distribution of electrons, sea of electrons. So then, of course, the total emission would not just be because of single electron-ion interaction, but integrating over the entire distribution. So what you will have to do is find out this angular area. So if this is the given ion, and this is one electron, we take a small excursion about the mean, about the impact parameter. So this is the impact parameter V of one electron. If we take dV, and if there is a density of electron involved, then there is again a finite amount of electrons in this small volume. So what I'm going to do is I'm taking angular rings. Oops. The ion is here, and these are the electrons. So I'm considering in angular rings how many electrons are there, and considering the interaction of all those electrons in this angular ring interacting with ion. Okay. So then what I have to do is, if there is not just a single ion but a distribution of ions, so I have to consider the total density of all ions. So multiply the previous formula by Ni. Okay. Now and then I have to multiply the total number density of electrons. So what is the total number density of electrons in this small angular ring? It will find the area of the angular ring, and then find the total volume is in unit time how many electrons are crossing the angular ring. So if you work everything out, you will find that this is the total any dV is the total volume multiplied by dA, and it's 2 pi dV, 2 pi dV. You multiply here, you will find that you will be left with this expression here. Okay. If you put the previous expression, you will get an integral like dV by B. B is the impact parameter. Now I'm integrating from 0 to infinity, but it will not be exactly 0, there will be limits. So we will be integrating from the minimum impact parameter to maximum impact parameter. So you finally end up with something like this. Again, the mathematical details are not important in this short lecture. What is important is to understand what are the dependencies on the physical properties of the system. I'll come to this logarithmic term later. But first let us look at how this is dependent on the densities. So the power emitted per unit volume, per unit frequency, per unit time is proportional to the density of the electrons and density of the ion. So if the electrons and ions are similar density, this is n squared. This is a fundamental property of Bremsstrahl's equation. It depends square of the density on the plasma, on the ionized gas. Or if you want to be more accurate, it depends on any times n. Because depending on how much of the ionization has happened, if it's not just a hydrogen plasma, you can have complex elements, you can have more electrons than the ions, so that's why you have many times n. Now this logarithmic term is quite interesting because that gives you some added factors, which we will discuss now. So the B max, so the maximum height up to which we will get. Remember that in the previous formula, we had already seen that for omega tau larger than 1, the contribution of this power is 0, or very close to 0. It's e to the 1 minus omega tau. It's not exactly 0. We'll approximate that as 0. What is omega tau? Tau is B by B. So omega tau greater than 1, this one, gives you omega B by B greater than 1. So you naturally get an upper limit on B. So omega B by B, write it down. This is the maximum B that we can get, beyond which we will not get any emission. So we have an upper limit already. Right. Now let's talk about the lower limit. The lower limit is sort of a hand-wavy way of approaching it. There are two ways to approach the lower limit. One is to find when does the acceleration vector becomes comparable to the velocity itself, or change in the velocity becomes comparable to the velocity itself. Beyond that, it almost becomes like quantum scattering, because the scattering would be very large. So you have to go to the quantum mechanical limit. So if you get that, you get some constraint on the minimum velocity. Other is you just compare the kinetic energy and the potential energy of the charges. When that is true, this is called the Rydberg energy. If the Rydberg energy is reached, then you also get a lower limit on the P minimum. This is without considering quantum mechanical applications. So what are the two limits that we are changing here? In the classical case, when we are not considering uncertainty principle, one is when the change, so initially as I had discussed, the change in the trajectory is quite small. But if the change in the velocity becomes comparable to the acceleration vector itself, like this, or the change in the velocity becomes compared to the velocity itself, then the change in the trajectory is very large. So then we have to consider that a total, like a proper scattering phenomenon, which we'll see with later. So that gives you a P minimum here. If you want to go to the further quantum limit, just apply the uncertainty principle. And naturally, you have the momentum of the electron. You naturally have a length scale beyond which you cannot do empirically. You cannot push the length scale down to the ion itself. So, how do we do this practically? So, all of this gives you a logarithmic factor, which is called the dot factor. Now, the takeaway point I would want you to take away from this is the total emission depends on the square of the density and the dot factor. The concept of dot factor is very important because that appears in many such applications. And the dot factor is usually as a logarithm of some quantity. So in this particular case, it's a logarithm of B max by B min. So how do we decide which B min to use? We look up charts like this. We first compare what is the kinetic energy and how does it compare to the Rydberg energy. We also compare what is the frequency of the photon being emitted and how does it compare to the Hawking square. These charts have been thankfully prepared by several authors in the 70s. We look up the charts, find where my particular frequency and particular electron energy falls, and then use that particular beam. But this formula is not of practical use because what we have assumed here is a constant distribution of ions and constant distribution of electrons. In practice, of course, you will have a thermal distribution of electrons. So this is called thermal Bremsstrahlung. Now what we'll have to do is, you take whatever you obtained earlier, so distribution of ions and distribution of electrons, then assume that the distribution is a thermal distribution. So you have to integrate over the Maxwell-Boltzmann distribution. Okay, and then again, you get after some lot of algebra, you get again something like this. But now this is what we actually can observe when we observe Bremsstrahlung emission. I'll give an example shortly. How does it depend? It depends on square root of the temperature to the power minus half. So 1 by square root of T and N times Ni. And then this is cutoff factor, e to the power minus Hd by K. So for a given frequency, it depends something like this. If you integrate over all the frequencies, the total Bremsstrahlung emission, this is to be a standard integral, depends on the square root of the temperature. Okay, you will find that this will give you another kT, kT will cancel out and you have square root of on the top. So this is a very common property of Bremsstrahlung emission. It depends on square of the density and square root of the temperature. The spectrum depends on 1 by square root of T, but if you consider the total power, total cooling power of the thermal gas, the thermal ionized gas, it will be square root of temperature. One more interesting point. So when I was talking about black body radiation, I had said that if there's a thermal system, and if by some mechanism I can find the emission coefficient of the thermal system, I can naturally find the absorption coefficient of the thermal system. So I use this to find what is the absorption coefficient of this ionized plasma, thermal ionized plasma. So I have found that the emission coefficient gives rise to Bremsstrahlung emission, and that looks like this, the J nu, which I found out in the previous slide. Naturally, then I can extend it to find the absorption coefficient because J nu equals to alpha B, Kirchhoff's law. You find that the absorption coefficient then naturally looks like this, where it again depends on 1 by square root of T, N times Ni, and then there is this exponential fraction. Now you can of course then approximate the B nu into two terms, the Rayleigh genes and the Wien cutoff limits. For the two different limits, you will find that the absorption coefficient has different dependencies on the frequency. For the Rayleigh genes, cutoff, it looks something like this. So k to the power minus 3 by 2, 1, nu to the power minus 2. For the Wayne limit, it falls as nu to the power minus 3. Okay, so all of this are fine. What is important to take away is that very fact that we can do this. It's very simple. You find out J nu and you naturally find what is the absorption. Now, usually in exercises, what we give the students is even, okay, let me go to the next slide. Okay, so this is actually X-ray emission of the coma cluster. It's a cluster of galaxies. Cluster of galaxies have a lot of hot gas distributed around them. The temperatures of the gas are usually 10 power 6 to 10 power 7 Kelvin. So they can be, and if you convert 10 power 6 to 10 power 7 in terms of electron volts, you'll find that that falls in the X-ray domain in the frequencies. So this is an X-ray image using the Chandra telescope of the coma cluster. You see all this peak distribution here? That is a hot gas that is being emitting brainstorming emission being seen by Chandra. All these dots are galaxies. So the galaxies emit a hot ball of gas. So there is brainstorming emission happening. But there will also be absorption that will take place. So in the X-ray domain, this is the exercise I usually give for the PhD students here. If you find out what is absorption coefficient, you will find that all of this gas is optically transparent. It's optically thin. And if you go to radio frequencies, and if you look at not gas like this, because you see the absorption coefficient has a temperature difference, yeah. But if you go to slightly lower temperatures, the absorption is increased. Say 10,000 Kelvin. 10,000 Kelvin is the standard temperature of the ionized ISN gas. You will find that this becomes optically thick. So, in many of the cases, for example, an interesting point is there is synchrotron emission that can come. So, the radiation that is getting absorbed by this gas does not have to be thermal radiation. So, I have used this. It does not mean that the incoming radiation that is getting absorbed is a thermal radiation. So, this is just a basic property of the system. So, usually, what we again find in practice is, oh, I have the jet image. I can directly show you this. Yeah, this is a nice one. I don't have to draw the board. So I told you that let us focus on this part when I was talking about centrotron. You see this spectrum are curving like this. Why are they turning over? Why are they not continuing like this? If there is a formal distribution of electrons, they should have continued like this. The fact that they are not means there is some absorption taking place. So this is a common feature you see. So this particular case is synchrotron self-absorption. I'm not going into that. But in many of the radio frequencies, you see something like this, a turnover in the radio spectrum. This can be due to warm ionized gas lying along the path between the observer and the emitting mechanism. But the emitting mechanism can be a non-thermal mechanism, like synchrotron. So one common possibility, not for this particular case, again I must remind you, this is not a good example, but suppose this jet, whatever you see here, this is giving out synchrotron radiation like this. But what if there is a cloud of ionized gas along its path? Then the synchrotron radiation will have to pass through this cloud. If it is going to pass through this cloud, the emission will be absorbed due to thermal free absorption. So this is a common property where the absorption of the brainstorming process is applicable. But it is frequency dependent and temperature dependent. If you go to higher temperatures and higher frequencies, the absorption coefficient falls down. Okay, so that is one of the mechanisms, which is brainstorming emission. The takeaway point is, it is any thermal ionized gas will be emitting brainstorming emission, but it will also have an absorption coefficient associated with it. The temperature dependence of the total power is square root of the temperature and square of the density. Fine. Next is, I'm slowly going towards another mechanism that we see, scattering. I'll first deal with non-relativistic scattering and then go to relativistic scattering. So in the non-relativistic check, we will consider the incident. So scattering is what? When you have a electromagnetic radiation falling on a particle, they interact with one another and go in a different direction. So in the non-relativistic limit, I will not consider the radiation as photon. I'm just considering it as a wave-like radiation field. So if you have a radiation field incident on the electron here with some amplitude, then the electron will pick up the electric field and start to oscillate. If it is starting to oscillate, then you have a acceleration of the electron, R double dot. And if you have acceleration of electrons, you will have some radiation that will come out. So in practice, what we usually do for this is we find out the dipole moment, and that is why the dipole moment was used in the previous lecture, because it's easy. From the Thomson scattering, the dipole moment was attached to the development, but you do not need to consider the dipole moment. All you need to find out is the acceleration vector. So you just have the normal sinusoidal oscillation of electrons. You find out what is the acceleration. You find this is the standard dipole formula that we have done for the Larmor relation. You have a solid angle distribution of the power. So what is happening here is the electron is coming in, or the radiation is coming in one direction. The electron is oscillating, but this oscillation is giving out energy in all sorts of directions. And how does it look like if you have to recapitulate? If this is the acceleration vector, the distribution is like this. Now the acceleration vector is in this direction, so the distribution would be like this. So this is the acceleration vector, and this is the direction that is being observed. So this is theta now. Okay, so this is the power distribution. So now what we usually do in this particular case is we find out the time average. So there is a time involved here. I double down. So we will time average the quantum flux. Time average quantum flux is C by 8 pi d0 squared. There's a quantum flux is C by 4 pi. A half factor comes because you have this sine square omega t. If you average over time, you get a half factor. So C by 8 pi t squared. Now what we define, and this is a definition that we do, it is the power per unit solid angle is proportional to the time average quantum flux and an additional quantity. So this is called the scattering cross section. So in terms of the units, you can clearly identify what is happening here. So this is the power per unit solid angle, per unit volume of this. And the quantum flux is the energy per unit area. Okay. So then this one, if you work out the dimensions, you will find that sigma will have the dimensions of per unit area. Let me just work out the dimensions of this. So what I have here is d sigma d omega is called the scattering cross section. So given the interaction of the incident radiation field with the electron in a given direction, for how much of the scattering, how much of the energy is being transported. That is what this d sigma d omega gives. So if you want to kind of consider the total scattering, what is the total amount of scattering possible? You just integrate over the cross section, you get something like in terms of, you get an expression in terms of the fundamental constants. It's called 8 pi by 3 r naught square. R naught is the classical electron radius, which is defined as x squared by x squared. Let me see if I have one more slide here. No, I completely go to common. In practice, what we also do is find out the polarization involved with Thomson scattering, but I will not discuss that in this lecture now. But let's just focus on one of the key takeaway points from this. One is it has to be non-relativistic. Incident radiation, when it's interacting with slowly moving electrons, then you have Compton scattering. The total cross section is a fundamental constant, 6.65 10 power minus 25. This is very important. So if you want to understand, so suppose there is a radiation falling from somewhere and it's interacting with some matter or a gas of electrons. What is the nature of interaction? What is the optical depth or the absorption coefficient? If you remember, the absorption coefficient, let's go to the very beginning of what we discussed. I will upload the slides today if anybody wants to follow this up. Remember the absorption coefficient alpha is n times sigma A. So this sigma, the scattering that we are talking about, can be Thomson scattering. And if you know the density, you know what is the absorption coefficient. So any incident energy will interact with the gas. So I'm not sure if somebody will teach you about the Eddington luminosity or the Eddington limit, but it may happen that when you have incident radiation, so when incident radiation going out from the surface of a star, now there's matter also falling towards the star because of gravity. The radiation and matter can interact. How will they interact? By this Thomson scattering. So there is a finite cross section of interaction. And then they will transfer momentum. So the radiation can balance the infall due to gravity. And in this process, the way the momentum is transferred by the radiation field to the gas will be the Thomson scattering. And so then you will need to understand the concept of the Thomson scattering and Thomson scattering cross section. Another important point is this R naught quantity. It's called the classical electron radius. How does it come? E squared by R equals to mc squared. It's like comparing the response energy to the electrostatic potential energy. This classical electron radius, although it's just rearrangement of the fundamental constants, it's a very handy tool to use in some expressions because you can simplify expressions, especially for the synchrotron expressions. If you represent them in terms of the classical electron radius, you don't have to worry about the CGS and the SI units anymore because it becomes unit invariant. Okay, so that is Thomson scattering. So we have a very quick introduction to Thomson scattering. Last is we'll talk about Compton scattering. So these are more energetic photons interacting with electrons, then bouncing off the electrons in a different direction. So what we'll do is we'll go first to the rest frame of the electron to keep it simple. Electron is initially at rest. The photon, now I'm considering a photon, so I'll go to the proper special relativistic formula, conserve the momentum, and conserve the energy, and find out the total. Again, I guess when working on special relativity, you must have gone through this exercise of this scattering. This is not in bachelor's, I think. But in any case, the photon comes, the photon is scattered in a different direction. Now the electron also picks up some energy. So all you have to do is find out the initial set of co-momentum, the final set of co-momentum, and write the conservation of momentum and the conservation of energy. If you write all of this down, you can do this as a fun exercise. You will find that the scattered energy of the photon, E1 prime, can be expressed in terms of the incident energy of the photon, epsilon prime, and the angle of scattering, theta 1 prime. I'm talking about everything in prime coordinates because this is the S frame of the electron. It looks something like this. It's just energy conservation and momentum conservation. It looks like this. Okay? So it is epsilon prime divided by 1 plus epsilon prime by mc squared and 1 minus cos theta. Now, if I go to the limit where epsilon prime, which is the incident energy of the photon, is much smaller than the rest mass energy of the electron. Okay? So this fraction here is very small. Then I can effectively ignore all the cos theta terms here. If this is the case, then in the rest frame of the electron, the energy of the incident photon does not change, or changes in a very small amount, which is like almost negligible. The change is very negligible. So this is called almost like an elastic condition, where the incident and particles energy does not change. So E1 prime is equals to epsilon prime. Now you can think, so what's happening? So what's special about this? Photon comes, goes away. So how is the energy distribution of spectrum changing? All of this was being done in the electron rest frame. As soon as you do some frame transformation, find that things become more interesting. So go to the last frame, the electron is moving with some velocity. Now if the electron also has high velocities or relativistic velocities, then it becomes more interesting. You have the photon coming in here and then they scatter off. So to do this, first you have to boost to the electron restraint, do the scattering cross section and deboost from the electron restraint to the lab rate. This boosting and deboosting itself now gives you this additional term. So you boost electron restraint, assume there is elastic collision, then come back to the lab frame. You will find that the energy of the photon has changed. Simple relativistic transformations. Using the fact that this is elastic collisions. If you could not use elastic collision, then there was a problem. Then you have to go to quantum mechanical scattering, which I will not discuss, of course. So if you just work out this, you will find that the final energy of the photon is not exactly the initial energy of the photon in the lab frame. It is 1 minus beta cos theta and 1 minus beta cos theta 1. So you can see there is an angle of both, the incident angle and the final angle, both are present in this. So of course there are two limits that are possible. What if the photon approaches from the front? So theta equals to pi. Then and is so you have to impose both these two angles by hand. So photon approaches from the front, so theta equals to pi, and is reflected along the electron. So electron is going like this, photon comes and goes back. To put this, you'll find that E equals to 1 plus beta and 1 minus beta. If you work out if it's a highly relativistic system, you can expand these expressions in terms of the gamma of the electron. You will find that it becomes 4 gamma squared E. This is very powerful. If there is an incident photon colliding with a relativistic electron, then its energy can increase. The maximum possible energy increase is 4 gamma squared. So if the gamma is 10, which is plausible, this becomes 100. There's 100 times gain in the energy of the photon. And so on, because I talked about this power law distribution of electrons now, going from 100 to 10 power 6. All of this, if they're interacting with some distribution of photons, then they'll also get scattered like this. But in the opposite direction, this is called a tail-on collision. The photon, so electron is moving this way, photon comes and catches up with the electron, collides and then goes back. The tail-on collision, photon approaches from behind, theta equals 0, and then is reflected opposite to the electron, theta equals to pi. Then the electron and the photon can actually lose energy. So in a counter scattering, photons can both gain energy and lose energy. All of this with the assumption of elastic collision, that is, in the rest frame of the electron, the photon does not change, energy does not change too much. Why? Because the incident energy of the photon is much smaller than the response energy. This is the takeaway. So quantum scattering has the potential to change your spectrum. How does it change the spectrum? I just have a figure now. Of course, this entire set takes about a full 3-4 lectures, so I'm condensing it shortly. So this is a practical application of quantum scattering. What is happening here? This is an accretion disk. I'm not sure if you've heard of it so far. If you have, then this is so suppose in the center there's a small stellar mass black hole, and there's a gas which, and since there's an angular momentum, it's not falling spherical, it is falling in terms of accretion disk. If it's accretion disk, then there are photons. So this is thermal distribution of gas. So there is a black body distribution. So with not a single temperature, because each ring of the accretion disk has a defined temperature. So it's called a multi-black body distribution. But suppose from one given radius, you have some emission. So usually in this system, all of this thermal distribution of gas is surrounded by a very hot plasma. It's called a corona, similar to what we have for the sun. You have a corona in the sun. This hot plasma is extremely hot, temperature of 10 power 7 Kelvin or so. And the electron temperatures are in the orders of 50 keV, so kiloelectron volts. So any photon that is coming out from this accretion disk will then go and scatter with this object and go up. So when we look at the spectrum in the X-ray observations, so this is the log of the frequency, frequency log space, and this is the spectrum. The accretion disk spectrums follow something like this. Okay, because it has a weight cut. These photons are the soft photons, so this is usually say 1 keV. It's 1 keV. It usually peaks around 1 keV, 1 to 2 keV. These photons, less than 1 keV are called soft photons. 2 keV and higher are called hard photons. Will they interact with this gas of clouds to produce a power law tail like this? So the total spectrum is usually represented as an initial black body. So what we can do is that we can fit a power law and then have a convolution of both the spectrum, efficient disk plus power law, to fit the total spectrum. So I think if somebody discusses extra strong, we will give this in more detail. But this extended tail going into high, not on high frequencies, often very hard frequencies, 50 kV or 100 kV, that can be due to counter interaction. Of course, I'm simplifying things a lot because then you have to consider something called the thermal quantization, where you have a thermal distribution of electrons interacting with, so thermal electron gas interacting with quantity. But this is a practical application where the energy of the photon, although it's small, it can get boosted to very high energies. What I'm showing here is also another interesting part. Since it's in the figure, let me also discuss that. All of this quantum interaction of the quantized photons after the interaction will come and hit the accretion disk and go back to the observer. So the observer will see three components. One, direct emission from the accretion disk, which gives rise to this black body spectrum. This quantized emission, which gives you the extended power law tail going to very high frequency. And another reflection spectrum. This quantized emission reflects from the accretion to goes back. So the total spectrum will be a convolution of all of these, and it's quite difficult to disentangle what contributes what. So you have to scan over a parameter space with changing the parameters in small steps to see what gives you the best fit to the spectrum. Okay, so I will end here. Just pause for a few minutes to see if there are any questions. This was a very rushed tour of radiative processes, but I guess I have stressed enough the key takeaways that you should focus on, because that will help you to identify some of the future lectures in this semester and connect with the different astrophysical phenomena, because you see the different emission mechanisms appear in different domains of astronomy. When you look at thermal distribution, you see a black body spectrum. Black body is very ubiquitous. You can find X-ray astronomy, optical astronomy, everywhere. Synchrotron emission is mostly found in radio astronomy. That is not always the case. If you go to gamma ray astronomy and look at emission from gamma ray burst, GRBs, that's synchrotron. But why in gamma ray? Because synchrotron is usually a low frequency phenomenon. In the rest frame of the fast moving flow of the gamma ray jet, that is synchrotron. You come to the left frame, there's a Doppler density involved. So the frequencies shift. So when we see the emission from the synchrotron rest frame in the gamma rays, we see that in the gamma ray burst, or jets from dying stars or colliding neutron stars, let's say, you see them in gamma rays. So that is one application of synchrotron. Bremsstrahlung, if you do cluster of galaxies, you look at extra emission from clusters of galaxies, Bremsstrahlung is the standard mechanism. Any thermal gas beyond 1 billion Kelvin will have Bremsstrahlung. If you look at the atomic cooling, so the atomic cooling curve, so this is cooling, I don't know, maybe this is a bit advanced for you. So what this shows you is due to atomic transitions, there is loss of energy. Now, in a standard solar or standard composition of the oxygen, etc., etc., this peak happens at 10.5. This is 10,000, and so on. But as soon as you come here, it just becomes a power law characteristic. And the slope of this power law is 1/2. So this transition happens at 10 power 6. So below 10 power 6, all sorts of atomic lines give you the emission. So cooling is what amount of energy is lost by a given volume of gas, and energy lost is what we see, the radiation. So cooling gives you an approximate measure of the cooling rate of the gas, of any ionized gas, or the amount of radiation we see for a gas at this temperature. But what I wanted to focus on was this part. So in the cooling curves, you usually have a power law tail that is due to Bremsstrahlung. So that is one application of Bremsstrahlung. And when I come to Compton's scattering, we consider high energy photons interacting with electrons. And also, if the electrons are of higher energies, relativistic electrons, then we can have a boost. Okay, so if there are no questions, I'll end the lecture here. Yes. 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 Why you see the jets? Very good question. A very standard question we get actually. So suppose this is the accretion disk. You have the black hole here. So if all of this matter goes and falls directly into the accretion disk, you will not see anything. What happens is there are two mechanisms by which you can see the jet. So if this is the black hole, accretion disk. So before the matter falls in the accretion disk, there are magnetic fields involved. So suppose these magnetic fields are anchored onto the accretion disk, vertical magnetic fields. Now, if these are rotating, the magnetic fields are getting twisted. So these magnetic fields not remain just purely vertical fields; they get dragged like this. So they become a spiral. As they become a spiral, they pick up matter from the accretion disk, carry them along with them, and from very far away, what you see is a total outflow that is happening.
Can you say that the magnetic field is stronger than the gravity of the
Not here, far away from the innermost radius. Before it reaches the innermost radius, then the magnetic pressures are large enough. Of course, once it becomes close to the innermost radius, then it cannot. But there is another caveat there. So this is called winds or outflows launched by the disk. This mechanism is called Blandford Payne mechanism. But there is another mechanism. Now this black hole that we drew, if it is a rotating black hole, there is small. So if this is the event horizon, there is a small region outside of the event horizon. If you pull the curve actually, where the magnetic fields can exist. In this point, the magnetic fields are again dragged by the frame gravity of the black hole itself. Then they get twisted. If you go to the locally, if you just do a relativistic transformation, if you have moving magnetic fields, you have electric fields. Right? If you have electric fields, then some charged particles come there, that will get accelerated. That charged particle acceleration will be radiation. So essentially what you get here because of the frame dragging, you get quantum flux. So then another mechanism is right from the very close to the black hole, before the matter falls into the black hole, we have a quantum flux that goes vertically upwards. This is called the Blandford-Snide mechanism. Snide spelling is C. It's magic, but it's pronounced as light. So there are two mechanisms. The matter, once it goes inside the black hole, of course, will not come out. But the outflows form before the matter falls inside the black hole. Any other question?
Is the reflection spectrum and continuum same? Like what they
No. So that is the thing. The continuum spectrum will give you a power law. The reflection spectrum, again, there is some scattering involved with the accretion disk. So the shape of the spectrum changes because it depends on what part of the accretion disk is interacting with. So this reflection spectrum will scan through the entire temperature distribution of the accretion disk and the morphology of the spectrum. So For the reflection spectrum, you input a power law spectrum interacting with thermal photons in the diffusion disk, and that is called reprocessed emission. The nature of the spectrum changes.
Do they absorb and then re-emit?
It can also be considered static because they're high energy photons. Any other question?
What is the cause of the magnetic field over here? The black hole?
That is not known. That is sort of an assumption. You see, if there are local currents involved, you can create magnetic fields. If the currents are from the diffusion disk itself, that itself will create magnetic fields. If the currents are from far away, if the entire system is embedded in a large scale magnetic field, well, you can have magnetic field. So whether these magnetic fields are generated by the diffusion flow, or if the magnetic fields are large scale, that is still an open question for today. So people do simulations to find if you have a turbulent distribution of magnetic field that is already falling in, can it self-organize into large-scale vertical fields, and that itself will lose checks. Otherwise, other simulations just assume a large-scale field exists from before, and as the material falls in, it bounces the outcomes. That's still an open question, but yes, it's an important question. Any other question? Okay, thank you.
फोटोग्राफर आ रहे हैं मैं ढूंढती हूँ
अभी रिकॉर्डिंग चल रहा है।
आज तो नहीं आ रही रिकॉर्डिंग हो रहा है Sorry, guys. I'm so sorry, guys.
Hey, mute भी नहीं है.
तभी तो sorry बोला ना.
वो उसको बोल दे अनिकेत
क्या?
इसको काले